All right. Good afternoon, everyone. My name is Eric Werness from NVIDIA, and I'm going to be presenting on execution reordering for ray tracing performance. And so I'm going to be starting off giving just an overview of the motivation for this, why we want to do this, then give an overview of the API, and then move on to example code and best practices. So this presentation is about an upcoming EXT extension, kind of presented with approval of the ray tracing TSG that's developing it. But because it is proposed, it's not entirely final, and some details may change, though it's mostly locked in at this point. So why are we going through and doing all of this? As we saw kind of in Hugo's talk this morning, GPUs can do incoherent work, but they're not at their happiest when they're doing incoherent work. A coherent GPU is a fast GPU, is a happy GPU. And so you want to have this coherence both in control flow with convergence to keep the subgroups full, keep your groups full at all the different levels of hierarchy, doing similar code where the code is similar. And you also want coherent memory accesses because each of these different levels, there's different levels of caches as well. And that's all kind of on basic GPUs. And then for things like cooperative vectors, you'll hear about more from Jeff in a couple of days, those techniques benefit even more, where having the entire subgroup working on the same thing hits a fast path. And for ray tracing in particular, this gives a lot of benefit for complex material systems on large scenes where the inherent divergence of the scene is very large. And so one big question that one might ask about this is, why is there a new extension? So after all, the original ray tracing pipeline API includes, in its definition, support for implicit reordering, including these shader call points and reorder points, which were newly introduced by that extension. It limited the definition of ray tracing launch grouping with to kind of make that implicit, explicit indexing of the shader groups, and these other new definitions. So then what do we need on top of that? Well, for one thing, there's more information that we can provide to provide better locality with this new hit object API for invocation reordering. And also the explicit reorder point gives a little more flexibility in the application to decide when reordering is a benefit and when it isn't, as well as allowing more functionality that I'll talk about later in best practices for new things that you can do with the hit object, even without reordering. And so another question of why it's designed like this is, why is this new reordering functionality in ray tracing shaders, ray generation shaders specifically, rather than in general compute? Well, general compute, especially designed as it is in Vulkan as a very explicit API, has this explicitly defined thread grouping and work group memory. And the ray generation shader had already restricted those to allow better reordering initially. And so it's a better target, in the short term at least, for thread reordering for locality than trying to have a fully generic compute shader with all of the reordering locality. So now kind of to go over the overview of the API so that the code examples later will make sense. The hit object is a opaque handle, opaque similar to the ray query object if you're familiar with that one, that encapsulates intersection details and hit or miss state in this object. Can be declared in ray generation closest hit or miss with no extra storage qualifiers, right? It's only this hit object. And there are built-ins similar to the built-ins existing for ray pipelines or ray queries to extract the state of this hit object. It stores all of the information that you'd expect from the ray query, plus the added indexing information from ray pipelines to get to the correct shader. And so for the first thing you need to do with these new hit objects is to create and/or trace from them. And so a hit object can be in one of three high-level states. It can be empty, which has not been traced to, a miss, where a trace did not hit, it missed, and has the kind of miss shader information, and then a hit, where you have the primitive information of the hit as well as the hit shader group information in it. And each of those states, so the empty and miss states, you can explicitly record an object into those states. The hit state, you have to have done a trace. And once you have done a trace, the hit object moves into either the hit state with hit shader indexing information and hit information, or the miss state. And so there are two different ways in this extension to create a traced hit object. The first is the hit object trace array function, which is equivalent of the existing trace array function in array pipelines, but targeting a hit object, so that rather than fully executing the array pipeline, it only runs intersection in any hit, and then at the point of completion of the intersection loop, it returns back out to the array generation shader with the hit object updated to the correct state. And also there's the ability to create a hit object from a array query, so that you can have this interoperability between hit objects for reordering and array queries. And so the hit object, the array query information is extracted from this other object and put back into the hit object, along with shader attribute information, which is required for hit groups in traditional ray tracing pipelines. And next you have this whole set of get functions. And these are all parallel to the equivalent get functions in array pipeline or array query, where there's the set of state that's encapsulated in the object, such as world ray origin, object ray direction, the shader record buffer handle. And all of those can be extracted with the get function from the hit object. And so this, because you can extract this information at the point of intersection and before calling the shaders, this gives you the information you need to do custom shading logic or custom selection of hit groups based on the intersection details. And next, we're kind of getting into the meat of the extension, which are the functions to reorder based on information provided by the application and or in the hit object state. And so you can see there's three variants of the function here, providing both the hint bits, flexibly providing combinations of the hint bits in the hit object to do reordering. Reordering is only valid in array generation shaders because that is where we have kind of the top level view of all of the data. And so the hint and the hit object provide different bits of information into this key that's used for whatever reordering algorithm the implementation wants to use. And the ordering of these is defined, which is important in terms of most effectively using these bits. So most important is the shader ID calculated in the hit object for your hit group or your miss group. That's the high order bits of your comparison, the key. And the coherence hit that's provided with the kind of first or third functions that I show there, the explicit hint bits coming from the application, is included after the shader ID. And then after that is any other information that the application sees, the implementation sees fit to include from the hit object. That could be sublocation within the acceleration structure. It could be a geometric hash, whatever the implementation sees fit to use in its internal sorting. And the specification isn't particular about exactly how the reordering works to give the implementation most flexibility. So it could be a sort, it could be coarse bucketing, the extension doesn't say. And hopefully any implementation that's providing this will have kind of tested and confirmed that whatever reordering it does works effectively and is performant. And finally, for some implementations, there are fused functions provided, which are combinations of previously specified functions, such as trace and reorder together, trace, reorder, and execute shader together. And these are provided for some implementations where it's very important to have the fusion, and so it forces the fusion rather than having to hope that the compiler will detect it. And so now I'll go through some sample use cases and show the way that it can be useful to use this extension to get performance out of different rendering algorithms. So the first use case is a basic multi-bounce. This is just your normal path tracer. And this shows in the sample code in the next slide, this will show the basic decoupling of intersection from shading. You trace the ray with hit object trace ray, you capture the potential hit or the miss, then you reorder for coherence, and then if needed, you run the closest hit object, the closest hit shader in the hit group using hit object execute shader, which pulls the index out of the hit group. And then you repeat for multiple bounces as you trace your path through the scene. And so doing this explicit kind of reordering rather than relying on the any implicit reordering that the implementation does within traditional ray pipeline is most important when you want coherence at the end of the loop. And so here's the sample code here. This is in kind of the proposed exact syntax. So we declare at the top of the loop this hit object that we're going to be using as we go through the loop. And then trace array through the entire scene using dummy information here. And then in this case, there's no hint being provided. There's no application bits to say, I want you to reorder based on this. This is just asking the implementation to reorder based on the shader ID and any other spatial coherence information that's available in the hit object. And so if the hit object is a hit, then we can execute the shader there and then decide, okay, I'm continuing on for multiple bounces. And because you've reordered there, now all of the threads, because you've reordered above, all of the threads that hit in the hit object are together and are continuing to execute their hit shader and then move on to the next bounce together. Whereas all of the shaders, all of the intersections that are amiss are in the else case and are also similarly grouped together. And then later on in here, this is where any further code you can be. And that's where, like I said, the big benefit from doing the reordering separately is that now you've reordered all of your threads together so that any further code that you're doing, extra processing of the hits, post-processing, things like that, will be in a more coherent and convergent state. Second sample use case is if we're adding Russian roulette sampling to the classic multi-bounce example, right? The Russian roulette sampling is a classic technique where you can eliminate some of the samples based on guessing ahead of time. And it can be a useful technique for rendering in a path tracer, but it frequently leaves a poor occupancy as different threads drop out at different times. Because we're doing the sort already, adding another hint bit for this one estimation of whether we're going to continue the path or not is very close to free. We're already doing the sort. And so now we're just adding one more bit to the sort. And so if you have a limited bit size of your sort key on an implementation, maybe one bit of spatial information gets pushed off the bottom, but it's very cheap to do. And one nice thing about this is that because everything is still correct in this case, even if the reordering is wrong, you don't have to worry about the correctness of your estimate of the sampling decision. You can just mix it in, and the more correct it is, the better the performance is, but the correctness of the result is always guaranteed. And so here we can see a very similar code to before. You create the hit objects, trace it, and then the first thing you do after you've gotten this hit is to get the shader record buffer handle corresponding to the hit and fetch an albedo, just as an example. And now you can generate an estimate of, based on that albedo, am I going to be casting another ray? And combine that with, is this the last iteration of the thread, of the loop, right? Do we think we're going to continue on in the loop or going to exit the loop? And then based on that, we send down one more bit to reorder thread in the hint. So this is the variant of reorder thread where there's a hit object, a hint bit, and a number of hint bits. So you can see we're passing in the hit object, the hint, and it's one bit. And so this sorting is defined as the shader ID will always be sorted first, then our one hint bit next, and then any other information. And then you can see afterwards, it's basically the same path as before, except we've kind of we can decide for sure if we need the next bounce and continue on that way. I mean, obviously, this is a kind of dummy example, so we have the precise information, but if you assume that the calculation is more sophisticated in the real example, then it would make more sense there. Oh, I hit the wrong button. There we go. Another sample use case would be near field, far field tracing for convergence and locality. Large scenes, a technique that people often use for ray tracing is to split into near field and far field. So near field is the things in your room, in your nearby that you might interact with, and far field is things like the environment outside, where you still need to consider it, but it's further away and it's not going to interact as directly with the rendering view. So using invocation reorder, we can take advantage of this split of near field and far field to optimize for locality on the far field traces in particular. So you can trace your near field, reorder and shade the near field rays in one coalesced group, and then for the ones that missed in the near field, sample the far field. And so here is, again, a similar example, no loop this time because it's not a path tracer. We're just showing the basic operation of fetching from the two. So you can trace the ray into your near field hit object, reorder based on the information there. And because hit and miss is encoded in the shader ID, that's already going to be included as part of the sort key. And so no extra hint will be required. And now for the if test where we decide whether to trace into the far field or not, we should be coherent with similar work in the similar subgroups together. And this also shows an example of a case where the fused functions are useful and can be used. A lot of these you can't use the fused functions because we're adding conditionals in between. But in this case, for tracing the far field, you know it's all happening at once. So you can just use the single fused function that gives benefit on implementations that prefer the fused function. Another kind of smaller sample use case is common computations with hit coherence. So today, when you're doing a ray pipeline, everything goes into the one shader for the hit group. And because those are compiled separately, that code is actually separate and isn't going to be coherent because even if it's doing the same computation, you've compiled it 2 different times and it's actually a different code in the implementation. And so what you can do in this case by separating the frequency of the trace from the hit shader execution is to factor out either as a separate invocation or in this example, just as a function call in the ray generation shader, common code. So in this case, the example is tracing a ray into a hit object, reordering, because that's the whole point of the extension. And then you do this common global illumination cache lookup based on common parts of the hit. And that is going to be run coherently. And because it's a single function, should always be the same code across all subgroups. And then once you've done this common code, now you can fork off into all the different closest hit shaders, which are separate code. And so a few general best practices. This one is not really a best practice, but seemed to fit best in this section. Is just kind of other uses for hit object. The primary category that all of these fit into is you can change the frequency and the indexing between the hit and the invocation of the hit shader in a way that Ray Pipeline doesn't allow. So, for example, you can not execute closest hit after intersection. You can do this today with the skip flag, but that doesn't provide all the same hit information that you would get. So this is a way to do a hit, not run a shader, and get the hit information in a way that also integrates with any hit and intersection shader. You can also execute multiple closest hits after an intersection. So in the previous example, I was showing a way to call common code directly from the ray generation shader, but an alternate way to implement that would be to synthetically point it at a hit group that does the common code, execute the common code with that hit group, and then come back and repoint it back at the original hit group and execute that again. This also gives the ability to do custom shader table indexing and visibility. Visibility in particular into Ray Pipeline shader binding table indexing has been a big issue. And so I suspect that for some people, this will actually be a major use case is just the ability to see before calling into it what the indexing is and what it returned for the shader hit group. When to use and not to use reorder. And this is an interesting question, and unfortunately has a fairly empirical answer, is sometimes it's going to end up being worth it and sometimes it's not, and you just have to benchmark. There are a few heuristics you can use when you're looking at it to try and decide if it might be worth it or not. If you have something like a path tracing workload where you're bouncing all over the scene and there's very little coherence already, that could be helpful. If you have more materials, it's more likely to be helpful. It's less helpful if you're not doing much. If you're just doing basic ambient occlusion, where the only output of the trace command is a hit or a miss, it's not going to be as much use, unless you just want it as general reordering. Live state is very important. Live state's important today already for ray tracing pipelines, because if an implementation is choosing to reorder, it already has to deal with the live state across the reorder call. But now that we have this explicit reorder point, it's even more visible to the application where it's important to optimize the live state. And so you want to give the implementation the ability to, as much as possible, rematerialize, have as little live state as possible live across the reorder call, and of course make sure that your memory usage is correct with reordering, because you might end up in a different place. You need to look at, there's already access bits defined in the ray pipeline for what you need to do to ensure coherence, and it's now more important with more reordering to make sure that the application access patterns obey the required read-write dependencies. And finally, use coherence hint bits carefully. So it's expected that in most implementations, whatever kind of bucketing or sorting or other reordering that they're doing is going to be on a very finite sized key in general. And part of the reason that we want to define the ordering those, that I kind of belabored a bit earlier, of shader ID, hint bits, other information, is to allow an application to know when it doesn't need to use hint bits. So you don't want to use the coherent hint bits to duplicate any information that is already implied by the shader ID, right? So even if it's not isomorphic to your shader ID, if you have half your shader IDs with the hint bit as 1 and half the hint bit is 0, that's still duplicative, and you don't want to include that hint bit in the sorting key. And finally, just in general, you want to use the minimum number of hint bits. Basically similar to what I said before. Yeah, it's just these are valuable bits to use. All right, and I forgot to say questions on this one, but that is always implied. Everyone knows how these presentations end.
I have a question. So since the reordering depends on the hit object, I usually only get that when I have like any hit shaders in my pipeline. I usually get that after all the any hits have been already called.
Mm-hmm.
So do I get any reordering behind the scenes for any hit shaders, or is that not possible?
The extension doesn't say, right? An implementation is allowed, and any kind of invisible side effects are allowed. Right now, the pipeline spec doesn't say where these other shader invocations happen. And so this is more about defining a bit more about reordering within the ray generation. So it doesn't touch how any hit or intersection shaders, which are called within the traversal loop, are done. That's all as it is before.
Thanks. And second question, you mentioned that we should use like the custom hint bits, shouldn't use too much of the custom hint bits. Does it already use like the geometry ID for the reordering internally?
Implementation specific, but if it does, that would be below the hint bits that are provided. Right, and so what the specification says right now, to try to give the right amount of guidance, is shader ID first, hint bits second, and then anything else from the hit object third. And so geometry ID is certainly something that you would, one of the things you would expect an implementation to use, but it is not required. And so if that is particularly important for your application, you should probably put that in your hint bits.
All right, thanks a lot.
Thank you. My question is about basically what this extension covers. We've been seeing GLSL shader code, and I assume there are SPIR-V entry points basically behind that. But it is an actual Vulkan extension in EXT state.
Yeah, it is. It is a pending EXT, just to be precise about that.
Pardon my ignorance. It's building on top of the ray tracing pipeline extension, which is a KHR.
Yeah.
So is it rather a technical or political issue that led to this being EXT and not KHR? And also, what is required on the host side? Do I need to enable this extension? Because it seems to be solely shader entry points that deal with the reordering. Can I just use it in an existing application by providing different SPIR-V? Do I have to actually enable this extension or query some support? Will there be knobs to turn?
Yeah, so I mean, there's obviously a feature bit like with every other Vulkan extension. So you need to, at minimum, do that in the API, is turn on the feature. As for EXT versus KHR, it's basically just it felt like the right level to have it, right? Because it wasn't, it just, no one really needed it to be KHR. And so generally speaking, what we've been doing in that subgroup is just EXT is the right step if it's not important that it be KHR, basically. I don't think I suspect this is one that at some point will be promoted with minimal changes, but right now it's EXT. Give people some time to implement it, play with it, make sure we don't want to do any fixes before we promote it to KHR.
Thank you.
What scale of reordering are you expecting to see on this? Is it going to be just a warp's worth of data that's reordered, or are we going to have massive packets of data that are going to be reordered? We already have some ray tracing code, and it does more than one level of ray tracing. So if it's going to be a warp level, it might not be worth us moving the multi-level back into a single level because it's only affecting the ray gen. So just an idea of how much we can gain from this.
Right. And I think, and again, this is something where the specification kind of intentionally doesn't say it's not required to reorder at any particular level. All that is required is that for it do some reordering and that the ordering of the keys is such. I would expect that most implementations would be doing something large, right, as much as possible, just because that's where you get a lot of the locality is really, especially once you're doing bouncing all over the scene in a path tracer, you're all over the place and you really need to cast a wide net if you want to get any kind of locality. So I think that's a reasonable expectation, but is not guaranteed.
I could just shout that. So I know you said this extension is only for the ray tracing shaders, but can you see a world where reordering threads might come to compute?
Yeah, well, it's like I said in the third slide, I think it was, you would have to change compute somehow for it to really make sense, right? Because you have these defined dispatch shapes, you have defined workgroup memory where everyone's been reading and writing to their own locations, and now you reorder. Well, and so now what does that mean? Do you just assume, do you have to say, okay, you know what, your thread is now somewhere else, good luck. Maybe you do. I think right now nobody has looked at that, but it seems like something that is technically doable and might be interesting. But at the same time, a ray generation shader that doesn't trace rays but uses just the reorder with hint is probably mostly what that compute reordering would look like. Right, you just have to have the support for ray pipelines, even though you're not tracing any rays. But whatever algorithm you would be doing in compute, unless it used workgroup memory and somehow handled the remapping behind the scenes, you should be able to do an array generation